Thank you for the introduction. First, I would like to thank the organizers for inviting me to this wonderful conference. In this talk, I will tell you about a family of Poincaré series. Let G be a connected semi-simple Lie group with finite center. Let K be its maximal compact subgroup. And let pi be an integrable discrete series representation of G on a complex Hilbert space H. Recall that this means that pi is an irreducible unitary representation of G, and that for any pair of k finite vectors H and H prime in H, the corresponding matrix coefficient C sub H prime, obtained by taking the inner product of the orbit map of H against H prime, is integrable on the group G with respect to any fixed Herm measure on G. It is a real group. It is a, excuse me? Yeah, it is not p-adic. It is real. Yeah, so finally, let gamma be a discrete subgroup of G. It is well known that for all k finite vectors, H and H prime in HK, so k finite vectors in H, the Poincaré series P gamma C sub H prime, defined as the sum of the left translates of the matrix coefficient C sub H prime by the elements of the group gamma, converges absolutely and uniformly on compact subsets of G, and defines a function on G, which is of course left gamma invariant, but also smooth, right k finite, and Z of G finite, where Z of G is of course the center of the universal enveloping algebra of the complexified Lie algebra of the Lie group G. Moreover, this function belongs to the LP space on G modulo gamma for every p between 1 and infinity. If, moreover, G is the set of real points of a Zariski connected semi-simple algebraic group defined over Q let me denote this connected semi-simple algebraic group by beautiful G. And gamma is an arithmetic subgroup of beautiful G of Q. Then our Poincaré series defines a cuspidal automorphic form for the group gamma, of course. Dragan Milicic proved that such Poincaré series for a fixed representation pi and discrete subgroup gamma and a dense subspace of the pi isotypic component of the right regular representation of G on the L2 space on G modulo gamma. If moreover this assumption holds, let me denote it by a symbol, then this component is an admissible representation of G because pi occurs with finite multiplicity in it, in L2G modulo gamma. So the only GK submodule of K finite vectors that is dense in this component is the whole GK module of K finite vectors of the component. Thus, if the assumption hard holds, then our linear span equals the whole GK module of K finite vectors in the pi isotypic component of L2G modulo gamma. Thus, many cuspidal automorphic forms that are interesting can be described by our Poincaré series. In this talk, I would like to discuss two simple questions about this Poincaré series that have quite simple answers, at least in some cases, and analyze how these answers can be interpreted in, for example, the space of modular forms. The first question concerns the Peterson inner product of two of our Poincaré series. In order to state it precisely, let us fix 4 K finite vectors in H. Let's call them V, V prime, H, and H prime. We want to compute the inner product of the Poincaré series attached to these two matrix coefficients. Of course, it is the inner product in the L2 space on G modulo gamma. In the case when gamma is the trivial group, this inner product is given by the Schur orthogonality relations. Which states that the inner product of the matrix coefficients C sub HH prime and C sub VV prime in L2G equals 1 over d of pi, where d of pi is the formal degree of pi, times the inner product of H against V, times the inner product of V prime against H prime. It turns out that in the general case, the formula is very similar. We again have on the right-hand side 1 over the formal degree of phi times the inner product of h and v. And the third factor is the value of the Poincaré series of the matrix coefficient C sub v prime h prime at the neutral element of G. Whereas this formula looks like a well-known classical result, I was not able to find it mentioned anywhere in the literature. So let me give you a very quick sketch of proof, which is quite elementary. So one can check very easily that sure orthogonality relations can be written in the equivalent way as follows. R of the complex conjugate of the matrix coefficient C sub v prime acting on C sub h prime equals 1 over d of phi times the inner product of f of h and v times the matrix coefficient C sub v prime h prime. This linear operator is, of course, the standard action of an element of L1G on the representation space. And the thing is, if we attack this by the Poincaré series operator, we'll obtain this. And then if we evaluate at the neutral element of G, we'll get this. Now here one has to be careful. This here is an element of L to G. So it is not a function. This evaluation does not make sense because this is like equivalence class of functions, but the thing is this equivalence class of functions has a unique continuous function in it, and it is this continuous function that is its Poincaré series, which is also a continuous function which gets evaluated at the neutral element of G. Now, the right-hand side is exactly what we want to get on the right-hand side, and the left-hand side can be shown quite easily to be equal to this. The only slippery part is that one has to put the Poincaré series operator here first, and this can be done because one can show that P gamma, regarded as a GK module homomorphism from the GK module generated by this matrix coefficient, so we can write it like this, to the image of this under the operator extends to a continuous G equivariant linear operator from the closure of the domain in L to G, which can be written, of course, like this. To the closure of the codomain, the original codomain, in L to G modulo gamma. Moreover, this continuous G equivariant linear operator is either 0 or a G equivalence. So because it is continuous and G equivariant, it can commute with R of the complex conjugate of C sub v prime. And when once just follows the definitions and starts to writing this out, in a few rows you'll get this. So the proof is indeed elementary. Although this formula was not mentioned in the literature, at least to my knowledge until now, it was implicitly proved in one special case by Goran Mujic in 2012 in his work on the classical holomorphic cusp forms on the upper half plane. Let me tell you a bit about this. Let G be the group SO2R and K be group SO2. Gamma can be any discrete subgroup of SO2R that is of finite covolume in SO2R. Muich was looking essentially at this inner product while studying the cusp forms of weight M, which is integral and greater than or equal to 3. So the space of cusp forms of weight M for gamma can be most easily described as the space of holomorphic functions on the upper half plane, which I will denote by H, that are bounded in the sense that this function, the absolute value of f of z times the imaginary part of z to m half, is bounded and are invariant under the right action of the group gamma, where this right action is of course given by the famous formula, a matrix ABCD, which can be in SO2R actually, acts on the right on F in such a way that it produces the function f of az plus b over cz plus d multiplied by cz plus d to the minus m. So here it can be any function from H to C. ABCD can be any matrix in SO2R, and Z can be any point of the upper half plane. The space Sm gamma is well known to be a finite dimensional complex Hilbert space with respect to the Peterson inner product, which is convenient to normalize in the following way. We start with the factor 1 over the cardinality of the intersection of gamma with the group containing only plus and minus the identity matrix. And then we have the usual integral over H modulo gamma of f1 of z, the complex conjugate of f2 of z times the imaginary part of z to the m. And the measure is, of course, dx dy over y squared. The integrable discrete series of interest is almost the following one. The holomorphic discrete series of SO2R, which can be realized on a complex Hilbert space Hm of holomorphic functions from H to C that are square integrable in the sense that the integral of the absolute value of f of z squared when multiplied by y to the m is square integrable with respect to the SO2R invariant random measure on H. And the action of G is given very simply. G acts on F by this simple formula. Here we again have the action which I defined here. It is well known that the GK module of K finite vectors in Hm has as a basis the set of functions fkm indexed by non-negative integers k, where the function fkm is given by the formula 2I over z plus I to the m. I is the imaginary unit, of course, times z minus I over z plus I to the k. In fact, each of these functions f sub km spans a one-dimensional k isotypic component of age m that corresponds to the k-type chi sub minus m minus 2k, where the characters chi n of k are given by the following formula. Chi n acts on this matrix in the way that it produces e to the int. Okay, now we have the boring part, I guess. Now it is well known that the space of cusp forms S and gamma is unitarily isomorphic to a certain subspace of cuspidal automorphic forms on SO2R for gamma. More precisely, to obtain this subspace, we need to take the pi m star as a typical component of this representation, where pi m star is the contragradient representation of our holomorphic discrete series pi m. And then we need to look at the chi m isotypic component. So chi m is defined by this formula here. By the Milicic result that I mentioned in the beginning of my talk, this space can be described as the set of Poincaré series of the matrix coefficients of the representation pi m star, which have on the first place in the matrix coefficient the vector f sub 0 m star, where I use notation f star to denote the linear function on the age m obtained by taking the inner product against f. And on the second place, we can have any k-finite vector in age m star. Now, a very nice thing is that the matrix coefficients that are interesting here are given by a very simple formula. The matrix coefficient C sub f0 m star f star is equal to the square of the norm of the function f sub 0 m, so this is the special case of this function in age m, multiplied by f sub f. And f sub f is exactly the function to which our cusp form f lifts. The cusp forms, it is given by the same rule, this f sub f, as the lift of the cusp forms to cuspidal automorphic forms on G. Ff of G is given by this simple formula. Again, I is the imaginary unit. Now, using this, we see that this space is simply the space of the Poincaré series of the lifts of the elements in HMK, so in the space of k-finite vectors of HM, and then by taking this space back by applying the inverse of this unitary isomorphism, and noting that the rule is now that ff goes back to f, and from which it follows that the Poincaré series P gamma f sub f goes to a Poincaré series of the function f on the upper half plane, defined as the sum of over gamma of the summands which are obtained by acting by an element of gamma on the right on the function f. So this space goes to the space of Poincaré series of the functions f that belong to the GK module of k-finite vectors in Hn. In particular, the space of cusp forms of weight m for gamma is given by this Poincaré series. This is a well-known result, but it's nice to see it described in this way. And by applying our inner product formula, which I guess should be written here. So this is the inner product formula. If we apply it to the Poincaré series of our matrix coefficients, for which we know how to compute, and then if we take the result back to the space of the automorphic forms using the fact that our lift is unitary, we obtain the following classical result. For every function phi in Sm gamma, so for every cusp form of weight tensor gamma, the value of phi at the imaginary unit is equal to the inner product of phi and the Poincaré series T gamma f sub 0m multiplied by the formal degree of pi m. This formal degree is well known to be equal with the right choice of hard measure so maybe I won't write it. Okay, I will write it because I fixed the measure. Okay, so with the right choice of hard measure, this is equal to m minus 1 over 4 pi. And this here is a very well-known formula. From it, by applying it to the suitably chosen conjugates of the group gamma, we can obtain the more general formula, which gives the reproducing kernel function for the space Sm gamma. So we obtain the formula phi of z equals the inner product of phi with the formal degree of pi m, again, with the right choice of hard measure, this is minus 1 over 4 pi times the Poincaré series of 2I over the argument minus the complex conjugate of z to the m. This is the Peterson inner product, and this is the formula, a formula that holds for every z in H, and for every, of course, in S and gamma. So this is, once again, a very well-known formula, but I guess it is nice to see how it corresponds to the stuff on the level of cuspidal automorphic forms for gamma. So, yeah. One other thing I should mention is that this whole story in this example has been shown to generalize quite easily, but quite technically, so I decided not to talk about it in detail here, to cusp forms of half integral weight. For this, G has to be the real metaplectic cover of SL2R, the real metaplectic group, and also to vector-valued Ziegel cusp forms, so both scalar-valued and vector-valued. There, of course, G has to be the real symplectic group. So this is the first question about Poincaré series that I wanted to discuss. Do you have any questions, perhaps, at this point? Okay, so the second question is even simpler than computing the inner product of two Poincaré series. It is the question of the non-vanishing of Poincaré series. Namely, given two k-finite vectors in H. So we are back to our previous setting where H is the representation space of an integrable discrete series of a connected semi-simple real Lie group with finite center. So given two k-finite vectors and the H prime, we are interested in the question whether the Poincaré series P gamma C sub H prime or any discrete subgroup gamma of G that is fixed vanishes identically. Since our Poincaré series are cusped automorphic forms, this question is non-trivial, but it turns out that in certain cases that have sufficiently nice parameters, it can be answered in a positive way, in a negative way. So the Poincaré series does not vanish identically, using the following non-vanishing criterion, which was in its original form proved by Mujic in 2009, and I slightly strengthened it in 2018. In its most basic form, the criterion states the following. If we have an integrable function on a group G, which can be any connected semi-simple group with finite center, but even more generally, it could be any unimodular locally compact Hausdorff group that is second countable. So this is, the group G can be very, very general. Suppose that there exists a subset C of G that is Borel measurable and satisfies the following two conditions. On the one hand, the set C has to be big enough in the sense that the integral of the absolute value of phi over G, again with respect to a fixed Haar measure on G, is strictly greater than the integral of the absolute value of phi over the complement of C in G. But on the other hand, the set C should be small enough that the intersection of the product of the set C with the inverse of C, so this is a pointwise product, with the group gamma, which I haven't fixed it, but I fixed it in the beginning of the talk, so it's okay. Gamma can be any discrete subgroup of the group G. So if this intersection is trivial, contains only the neutral element of G, then we can conclude that the Poincaré series of the function phi, which is again just the sum of the left translates of the function phi by the element of the group gamma, and this Poincaré series is well known to converge absolutely almost everywhere on G and to define an element of the L1 space on G modulo gamma, but under this condition that a suitable Borel measurable subset C exists, we can conclude that the Poincaré series does not vanish identically. Let's go back to our example since we have written it out in so much detail. I'll show you how we can get some nice results in this setting. The idea is very simple. We just need to choose a nice set C for computations. And the idea is to use Cartan coordinates of G to get such a nice set with respect, over which we know how to integrate most nice functions, and the k-finite matrix coefficients of our representation by m are very nice functions. And we will be able to conclude the non-vanishing in certain cases. So again, let us go to the notation of the example. The group G is the group SO2R. The group K, its maximal compact subgroup, is fixed to be the group SO2. And the set C in our criterion can be chosen to be the product of the maximal compact subgroup K, the set of matrices that are diagonal with e to the t and e to the minus t on the diagonal, where t goes over a segment from 0 to R. And again, the third factor is the group K. Here, R has to be chosen as a suitable positive real number. The optimal R is not a nice number, but nice looking number, but it can be found quite easily. And for simplicity, let us fix a group gamma to be a principal congruent subgroup of SL2Z. So if we fix the level n, recall that this is just the set of matrices gamma in SL2Z that are congruent to the 2 times 2 identity matrix modulo n. So by applying the criterion, we showed that the Poincaré series of the function fkm, and recall this Poincaré series, fkm is in HMK, such series, such functions span this gk module of k-finite vectors. So this Poincaré series span the space of cusp points of weight n for gamma. That's why they are interesting. Does not vanish identically. And of course, this is equivalent to its lift by our unitary isomorphism to not vanish identically, so I can write this too. The lift will be the Poincaré series of the matrix coefficient f sub fkm. Both of these do not vanish identically if the level n of our group gamma is big enough. Also, the weight m has to be big enough, and the integer k has to be small enough. Okay, so here is the formula for the function fkm, so you can see what k is. So since I still have some time, let me show you a consequence with some numeric concrete results about the values of n, m, and k. So for example, the non-vanishing can be proved by using our criterion for the level n greater than or equal to 3. And whenever one of the following holds. K is 0, and n is strictly greater than 4 times 2 to the 1 over m minus 2 times the square root of 4 to the 1 over m minus 2 minus 1. So this is a good case also if the weight m is equal to 4 and the level n is strictly greater than 4 over 2 to the 1 over k plus 2 minus 2 to the minus 1 over k plus 2. The third case is when k is strictly greater than 0, but less than or equal to m minus 4. Here we have the non-vanishing whenever n is greater than or equal to 4 square roots of k plus 2 over m minus 2 times 1 plus k plus 2 over m minus 2. And another case is when k is strictly greater than m minus 4, but m minus 4 has to be strictly positive, so m has to be greater than 4. And we have a similar thing as this. N is greater than or equal to 4 square roots of k over m minus 4 times 1 plus k over m minus 4. So while this is not a very strong result, I mean, not many Poincaré series, if you get a feeling for the other non-vanishing results, can be shown to not vanish by this criterion. I mean, other techniques that are usually were geared to prove the non-vanishing of the classical Poincaré series, produce much nicer inequalities. Many more parameters are good. This is the only result that I know for the non-vanishing of the Poincaré series of the functions f sub km. Maybe that's because no one has tried to look at this series except for us, and they are not maybe that interesting in number theory, but they are interesting in representation theory because they correspond to the Poincaré series of the matrix coefficients. So yeah, I'll stop here. Thank you very much for your attention. By what? I'm really not sure about it. I do not know of a result about convergence, but maybe someone more experienced might know. I tried to find results on convergence for non-k finite vectors or for only discrete series that is not integrable, but I was not able to do it. Although some mathematicians told me that they think such results should exist, but I was not able to find it in the literature. I'll try once more, I guess soon. Oh yes, I forgot to mention that. Thank you very much for your questions. These non-vanishing results were also generalized to cusp forms of half-integral weight again, also Ziegel cusp forms, even vector-valued ones, and also very recently to holomorphic automorphic forms on irreducible bounded symmetric domains. I was at first thinking of maybe talking about that case here, but the notation is very ugly, so I decided to show you the ideas, and everything gets much more complicated notationally, but the ideas are the same, and the results are very, very similar in their form.
Which comes up.
Yes. I don't remember what it is. I should look at it in my paper, but the thing is, I look at R as a very technical number. I mean, the proof goes of the non-vanishing in that way that we work with a general R, and then in time we see what R should be, what is the best possible R, because it turns out that M is very much connected to a median of the beta distribution. So if it is strictly greater, no, it has to be strictly greater, I think, of the median of the beta distribution with certain parameters that are given in terms of K and M. I think there are some square roots in the formula and stuff, but it was not a nice formula. It is very much used, yes. Because of this R, we get these ugly numbers. And these are not exactly the values of R, but they are the median of the beta distribution. I have computed it numerically for some small values of the parameters. So this is obtained by actually estimating the median of the beta distribution using some papers from statistics. I guess the actual results are slightly stronger that hold, but they are in terms of the median of the beta distribution. This is obtained by using some very good estimates, I think, of the median. So it is not far from the best possible result by these techniques.